A perspective on interactive theorem provers in physics. Interactive theorem provers, ITPs, are a class of computer programming language which guarantee the correctness of mathematical definitions and theorems written into them. Within mathematics and artificial intelligence, the usage of ITPs is growing. In this perspective, I will discuss the best usage of ITPs within another area, physics, and motivate the existence of an open source community-run project for formalized physics results, PhysLean. 1. Introduction. Throughout history, physicists have used tools to both do and disseminate their work. These tools have in some cases shaped what it means to do physics at research level. An example of this is the printing press, which in the 1400s led to the dissemination of physics first through published books and then in the 1600s through journals. These journals in turn changed what it meant to do physics, introducing the concept of peer review. With the advent of computers, more tools appeared. For example, in the 1970s, Donald Kurth designed TeX, allowing authors to typeset their own mathematical manuscripts. This, along with another tool, the archive, gave us the ability to disseminate new work worldwide overnight. This solidified the concept of preprints within some areas of physics. Much more recently, the tool of artificial intelligence, AI models, has emerged. This is the first tool at our disposal which has the potential to create new ideas. The field of physics and academia more generally is currently undergoing a journey to understand how to best use this tool. Another tool which emerged with the advent of computers is the Interactive Theorem Prover, ITP. I'll give a brief description of an Interactive Theorem Prover here, with the details reserved for Section 2. An interactive theorem prover is a computer programming language, like Python, LaTeX, or Microsoft Word, that allows one to write mathematical definitions, or equivalently, computer functions, and state and prove theorems about them in such a way that mathematical correctness is guaranteed. The process of writing a definition or theorem into an ITP is often called formalizing or digitalizing that result. The fact that correctness is guaranteed is one of the main features that make ITPs so useful to work with. There are other features which include the ability for structured notation-independent searches, the ability to make contextual notes, the ability to develop automated theorem-proving tactics, the ability to use AI to aid in theorem-proving, see, for example, reference 1, and the ability to act as a bridge between theory and simulation. Given what ITPs do, it is not a surprise, therefore, that over the last decade or so, mathematicians and computer scientists have been using this tool. More recently, a handful of scientists, including the author, have also started to use ITPs. As with AI and any new tool, an important question is, how can we best use ITPs in physics in conjunction with the other tools we have available? Naturally, the answer to this question in physics will differ from the same question applied to mathematics or to computer science. This is because physics is not mathematics or computer science, and perhaps more importantly, the physics community is not the mathematics community or the computer science community. That said, the answer in physics should be guided from what is done in these other areas. In this perspective, I will argue for the following main thesis. The best way to get the most out of interactive theorem provers in physics is to 1. Have a single open source community run GitHub repository for formalized physics results with the following features. A. Interconnected theories. B. A philosophy of improvement rather than duplication. C. A consistent peer review system. D. The ability to have informal results. And E. The ability to integrate with knowledge resources. 2. When formalizing results, physicists should A. Include physics context. B. Build APIs based around data structures. C. Use AI tools in a controlled manner. And D. Build physics-based automated theorem-proven tactics around their data structures. The above thesis suggests an open source community-run project for all formalized physics results. Such a project has been started by the author and is called PhysLean, which is based on the Interactive Theorem Prover Lean 4. To prevent repeating the cumbersome wording, open source community-run project for all formalized physics results, in what follows I will use PhysLean as shorthand. However, note that the principles explored in this perspective extend beyond this project. I hope that a reader more familiar with the use of ITPs in mathematics will take away from this perspective the differences between formalization of mathematics and physics, and how these differences might affect best usage. The remainder of this perspective will be structured as follows. In section 2, I will give a general and high-level overview of ITPs. In section 3, I will discuss some of the existing uses of ITPs in physics as an illustration of what can be done. Sections 4 and 5 will argue from my main thesis given above. Section 2. What is an interactive theorem prover? An interactive theorem prover is a programming language. A comparison between an ITP and Python could be made, since ITPs let you write computer programs and executable functions. A comparison between ITPs and LaTeX or Microsoft Word can also be made, because you can write in an ITP mathematical definitions of theorems and their proofs. The difference between an ITP and, say, LaTeX is that an ITP checks for mathematical correctness. There are a number of different ITPs out there, for example, Lean, Rock, and Agda, all of which have slightly different features. In what follows, I will describe the rough workings of an ITP generally, though throughout this paper we will have a specific focus on Lean. The basic object in an ITP is a type. A type can be thought of as similar to a set, in the sense that it has elements. In fact, a type can be defined inductively by its elements. For example, the type of natural numbers is defined in Lean and most other ITPs as inductive nat. 0 is an element of nat. The successor of a natural number is an element of nat. This definition says that nat has an element 0 and that for every element n of nat, one has another distinct element, the successor of n. This inductively defines the natural numbers. Other common types include the type of integers, which is defined similarly to the type of natural numbers, the type of real numbers, and the type of complex numbers. There is also a type of types, whose terms are types. This gets into the complex issue of universes, which for most part can be ignored. In physics, one can have, for example, the type of electric fields, the type of Lagrangians, the types of fields in a theory, etc. The precise phrase for an element of a type is called a term, and it is usual to write the notation A:(T) to indicate that A is a term of type T. We say that the term A has type T. From types you can construct other types. For example, A to B is the type of functions from the type A to the type B. Another example is the type A cross B, which is the type of pairs of objects, one from A and one from B. Types can carry instances, for example, an instance of a vector space or a ring. The ITP can infer these instances, allowing one to, for example, use the notation A plus B for any two terms A and B of any type T carrying the instance of a vector space. A definition in Lean is a specification of a type T and a term of that type. The term might depend on other terms and types. For example, in Lean, one can have the following definition. Definition of a function that takes an element of A of type nat, produces a term of type nat, and is equal to 2 times by A. This corresponds to the definition of a term of type nat based on another term of type nat. This is actually equivalent to defining a term of type nat to nat as follows. The definition of f as a term of type nat to nat is equal to the function which takes a to 2 times by a. Despite being a mathematical definition within an ITP, this function would also be executable, allowing, for example, f of 2 to be calculated automatically. In Lean, one can also define objects through structure. A structure has multiple fields which can be of different types. For example, the product of two types, A times B, can be defined through structure with one field of type A and another field of type B. We'll see an explicit example of a structure in the next subsection. A similar construction to structure appears in other ITPs. An ITP knows the type of everything, and this is basically how it carries out its mathematical correctness checks. It checks that the types of terms are correct, given the context in which they appear. Now let us turn to theorems. The statement of a theorem is made by specifying a special class of types called prop. A proof of a theorem corresponds to specifying a term of the corresponding type. The key difference between a theorem and a definition, which is really down to a slight difference between a prop and a type, is that for a theorem, the term does not matter whilst it does for a definition. An example of a prop is propositional equality, defined in Lean as an inductive type of the structure T maps to prop, so it takes two elements of T, gives you a prop, and the only proof of that is reflexivity, where the two T's that you give it are the same. In some ITPs, there are tactics that help you in specifying terms of prop, in other words, proof theorems. These tactics manipulate the types present by applying previously known theorems and results. Importantly, by using tactics, it is possible to work using a high-level mathematics without much consideration of the underlying type theory present. This makes proof and results in an ITP not too dissimilar to proving them on pen and paper. It is worth noting here what makes ITPs different from one another. This is usually down to the underlying type theory used and additional axioms introduced. Section 3. Use of interactive theorem provers in physics. In this section, we discuss the use and in more detail the benefits of formalizing physics into Lean. Section 3.1. Existing formalizations. To give the reader an idea of what can be done within an ITP in physics, in this section I will give a brief review of some of the literature. First, I will detail some standalone publications, followed by an account of areas formalized within the Fisting project. Within classical mechanics, there has been an attempt to formalize Lagrangian mechanics with Isabelle/Hull within the thesis form. There have been two standalone publications on the formalization of results from optics. The first, reference 5, in the ITP Hull Light, covered parts of optical systems. The second is a bachelor's thesis, 6, which covered aspects of quantum optics. There are a number of standalone projects formalizing parts or aspects of special relativity. These include reference 7 in Rock and references 8, 9, and 10 in Isabelle's archive of formal proofs. The group of Tyler Josephson has been working in physical chemistry and have formalized aspects of thermodynamics in reference 11 and Leonard-Jones energy calculations in reference 12. The focus of these papers is in the direction of verified simulations. Turning to formalizations currently within Fisling, there is currently coverage in the following areas: electromagnetism, condensed matter physics, statistical mechanics, quantum mechanics, particle physics, and string theory. Some examples of explicit results formalized include Wick's theorem in particle physics, the quantum harmonic oscillator in quantum mechanics, Maxwell's equations in terms of functions and distributions, properties of the type binder model in condensed matter physics, the electrostatic properties of a point particle in 1 dimension and 3 dimensions, variational calculus and the proof of the Euler-Lagrange equations, the canonical ensemble, properties of the Higgs potential, index notation for representations of the Lorentz group including fermions, etc. To give an explicit example of a result formalized in Fisling, in the code block below, I give part of the file on the formalization of the Higgs potential. I do not expect the reader to understand all of the details here, as it is out of the scope of this perspective and is merely provided as an illustration. Given this, I'm going to skip the code block for the purposes of this audio version of the paper, and I'll skip to the paragraph that immediately follows it. The result potential is the input data of the Higgs potential, that is, the coefficient of the mass term v squared and the quartic term L. One can't use lambda in Lean as this has special meaning in type theory. The result potential dot to_fun is the potential, which takes as an input a Higgs field and a point in space-time. The results potential.Tooth-and-Smooth, which proves the smoothness of the Higgs potential, and potential.Is-Min-On if and only if field of Al-Pos, which proves the minima structure, make up the API around the potential for the Higgs field. It is noted that there are obvious improvements that one could make to this formalization by, for example, deriving the potential from an algebra consisting of the Higgs field and invariance under the standard model gauge group. See section 4.2 for a discussion around improvements. We invite the reader to view the Fisling repository for more examples of formalizations. The main point I would like the reader to take away from this subsection is that one can use ITPs to do high-level standard physics, and their use is not restricted to special areas of mathematics or, for example, axiomatizations. We will discuss what can and cannot be formalized in more detail in the next subsection. Section 3.2. What can and cannot be formalized. In the above section, we detailed results from physics that have already been formalized in an interactive theorem prover. I now wish to discuss more generally what results from physics can likely be formalized. It is well known that different areas of physics require and depend on different levels of mathematical rigor in their work. For example, in mathematical physics, this rigor is often absolute, whilst as one gets closer to experiments, the rigor required often decreases. The real determining factor of whether something in physics can be formalized or not is whether it permits a mathematically well-defined formulation. It is important to understand what this means, and to do this I will illustrate with a number of examples. The first example is setting a term in a Lagrangian to zero, as is often done when making approximations to make problems more tractable. In the above code snippet of the Higgs field, one could set mu squared in the potential equal to 0 by adding the hypothesis h mu squared equals 0 in the desired place. Such an approximation does not have a mathematically rigorous justification, but it does have a mathematically well-defined formulation, and therefore can easily be formalized in Lean. The second example is the path integral used in quantum field theory. It is well known that the path integral does not have a mathematically rigorous formulation. However, the process one undertakes to go from a Lagrangian to a scattering amplitude does have a mathematically well-defined formulation. In particular, the steps the physicist takes are all mathematically well-defined, even though they don't have a mathematically rigorous justification. The third and final example is one which would lead to difficulties in formalizations, which may or may not be surmountable. This example is related to Sorides paradox and is down to the use and definition of approximations. Physicists may approximate both 800 and 1200 by 1000 in an expression, but may not be comfortable approximating 1200 by 800. Because of this, it is difficult to give such an approximation a mathematically well-defined formulation, and it is therefore formulated into Lean. However, there are many areas and results of physics which do not rely on such approximations. It is worth adding to the above discussion that a lot of what can be formalized depends on a choice of starting point. Choosing a good starting point to a formalization can make it tractable, yet the formalization is still useful. The most natural and arguably best starting point for any formalization is an approximation of the underlying area. However, restricting to such starting points greatly limits the formalizations one can carry out right now, and postpones the other benefits discussed in the next subsection one can get from formalizing physics. Any formalization that one does in an ITP will be mathematically correct. However, it is important to note that an ITP does not prevent you from using a non-physically meaningful starting point of your formalization, the wrong definition of a key component, or adding assumptions which contradict one another. Also, it does not prevent you from proving results based on said starting points, key component, or assumptions. Indeed, from contradicting assumptions, one can prove anything. This is true even in mathematics, not just in physics. Thus, with any formalization, it is important that one checks the starting point, the definitions made, and the assumptions used before drawing a conclusion about the wider correctness of a result. A topic one may also worry about is the use of computational techniques in physics to prove theorems, e.g. with Mathematica or other computer algebra systems. It will be the subject of a future paper to show that such computational proofs can often be formalized in Lean with care, and to give an explicit example of this. Section 3.3 Benefits of Formalizing Physics. In the introduction of this paper, I briefly mentioned some of the benefits one can gain from formalizing results from physics into Lean. In this subsection, I will expand on this by focusing on the question, how can Lean fit into the physicist workflow? We'll see more examples of this in the next sections. First and foremost, physicists can use Lean to mathematically check their own results and see explicitly how it connects with other results in the literature. They can also use it to determine precisely what assumptions they've used and what are actually needed. Second, they can use Lean to search for results which may be needed in their own proof, or to learn about the existence of new results. Tools such as Google allow one to search based on mathematical structure and not just text. For example, searching Google for Higgs field will pull up any result dependent on this type, which may not necessarily be the case for text-based search. Third, they can use AI to help prove theorems. AI models have been increasingly used in Lean to help theorem proof. The main advantage of this is that the human and AI model can be completely sure of the mathematical, not physical, correctness of the results produced by the AI. I will discuss this more in section 5.3. Fourth, because Lean is a fully fledged programming language, one can write simulations and programs directly in Lean. These can use the exact same definitions that one used to prove proper mathematical theorems. Thus, you can talk about theory and simulation in the same consistent framework. Last, with careful planning and instruction, one can use Lean as a pedagogical tool to help teach physics and programming. This opens a whole new possibility for students and researchers to learn new subjects. It's important to make a brief remark on the differences between Lean and computer algebra systems. Computer algebra systems like Mathematica are very good at performing calculations, algebraic and symbolic manipulations, but one cannot prove theorems or define every mathematical structure in a computer algebra system. One can do these things in ITPs, and work has been done to improve the computer algebra nature of ITPs. Section 4. Arguing for PhysLean. The key component of the thesis of this perspective is the project PhysLean. The inspiration for such a project comes from open source projects in computer science and the project MathLib. MathLib is an open source community-run project to formalize results from mathematics into the Interactive Theorem Prover, Lean. However, it is not the case that all formalized results from mathematics end up in MathLib. This is in part due to the use of different ITPs within some communities of mathematicians. For example, mathematicians working on homotopy type theory or adjacent areas are naturally going to use an ITP which is based on this specific type theory, which Lean, for example, isn't. Thus the question arises, does using one ITP throughout physics suffice? In my opinion, the answer to this question is yes, for the simple reason that physicists rarely rely on areas of mathematics like homotopy type theory, where different use would be justified. Therefore, I feel that a consistent ITP can and should be chosen in all areas of physics, and due to the presence of MathLib, with its focus on classical mathematics, it seems natural that the ITP used should be Lean. One may wonder at this point why we need PhysLean if we already have MathLib, and could the results from PhysLean not go into MathLib? I believe the answer to this question is no, for the following reason. In physics, one cares about the physics context and mathematical context of a result. Compare this to mathematics, where one only cares about the mathematics context of a result. Including this physics context into a formalization, see section 5.1, to give the reader the underlying physics story is important and would not be applicable in MathLib. There is also the fact that MathLib requires a level of generality of results which is not applicable to all physics. For example, the explicit study of specific matrices related to physics, such as the CKM matrix in particle physics. In short, MATLAB and FISLEAN serve different fields and different community needs. Before arguing why I think the project FISLEAN should exist, let me address two possible downsides to having such a project, both of which are due to cultural aspects. The first downside is the following. Physicists, except experimental high-energy physicists, are used to working in small teams or as individuals, often in secret, and then publishing papers based on that work. Having an open source project like FISLEAN would require a more collaborative approach with, in some cases, work being added to the project piecemeal. I believe the necessary cultural shift can be undertaken to permit such collaborative work whilst also keeping the author's ability to write individual papers. This requires some sort of consensus to be formed within the community. The second counter-argument to having FISLEAN is down to different cultures between different areas of physics and how they may conflict with each other when working on the same project. I think we can optimistically learn from the mathematicians here that these potential conflicts is something that can be overcome. One potential way to prevent such conflicts is by having clear policies and principles which a project follows. Let me now turn to arguments for having FISLEAN. The main argument will be contained within the following subsections, where I will discuss the proposed features of such a repository. Most of these features are only possible with the existence of FISLEAN, whilst others would be extremely onerous to carry out without FISLEAN. Before describing these features, let me give one additional argument for FISLEAN. FISLEAN is a synergy of two tools, ITPs and GitHub. GitHub is usually the purview of the computer scientist, and we can learn from their use of it. Their usage is typically to have big open source community run projects or libraries. Think of the Python package SciPy, for example. There are three main reasons for this. Firstly, it keeps all similar results up to date with each other, using the same version of dependencies. Secondly, it makes it easier for users who only has to find, download, and learn to work with one library. Lastly, it allows standardization in, for example, naming, layout, etc., which can be enforced with automated scripts called GitHub workflows. For all of these reasons extend both to MATLAB and FISLEAN, and therefore motivate the existence and need for the latter. I'll now describe and argue for the main features of FISLEAN stated in the main thesis of this perspective. 4.1 Interconnected Theories. There are two possible ways one could organize FISLEAN. The first is to have each physical theory as a standalone formalization, built independently from all other theories. The second is to have each theory connected to one another, for example by depending on the same definitions and or with appropriate theorems. To illustrate these two approaches in more detail, let us give an example using electromagnetism. There are two theories of electromagnetism, one using standard vector calculus and the other arising from gauge field theory. In the first method of organization, these two theories will be developed independently from one another. In the second approach, they will be connected, for example, with a theorem that connects the first strength arising from the gauge field theory to the vector calculus definition of the electric and magnetic field. I believe that the second approach is the one that should be followed. However, it is worth considering the two advantages that the first approach may have over the second. To illustrate these two advantages, we continue to use the example of electromagnetism. The first advantage is the lightweight nature of the program. If I wanted to use the vector calculus version of electromagnetism in the first approach, this is all my computer would have to build. But in the second approach, it would have to build the whole of gauge field theory, which can be both time and memory consuming. The second advantage is related to ease of use. Most undergraduates know the vector calculus approach to electromagnetism, but few know the gauge field theory approach. In the first approach, there's no way that the undergraduate will get confused or stuck by something in gauge field theory. This is possible in the second approach. I state these two possible advantages of the first approach because if when following the second approach one thinks and understands these downsides, they can be mitigated with careful design and organization of the formalization. Aside from the obvious benefit the second approach has over the first, which is that one can more easily move between theories and see their connection, there is also a less obvious one related to axiomatization. In general, formalization of physics does not imply axiomatization, although it is one area where formalization can be useful. Let us use special relativity as an example, and suppose we have two axiomizations, A1 and A2 of special relativity, as well as the core undergraduate taught theory, C. Following the first approach above, one would formalize A1, A2 and C separately, whilst in the second approach one would be able to connect A1 to C and A2 to C, and also investigate the possible connections between A1 and A2 themselves. In an ideal situation, you would not want C tied to either or other axiomization, and this again requires careful design, especially if neither are considered standard. Section 4.2. Improve upon, not duplicate. Consider the following situation. Alice is formalizing a physical theory P. The theory P depends on some foundational material F that has previously been formalized by Bob, but Bob's formalization of F does not meet Alice's needs. What are Alice's options? Her first option is to completely reformalize F in a way that does meet her needs. This sort of behavior is followed in academic papers, where explanations of the same concept are repeated in lots of different papers, each fitting to different contexts and the idiosyncrasies of the authors. Alice's second option would be to modify or improve Bob's formalization of F, so that it does meet her needs. This is the approach taken with Wikipedia or the NLab, as well as with open source computer science projects. The author believes that when formalizing projects, one should have the philosophical view that the second approach is better due to two main advantages. The first is that it forces improvements to be simultaneously propagated through the whole library. This has the added benefit of ensuring and preserving compatibility between different areas of the library, which is related to the previous section on interconnected theories. The second advantage is that a third user, Charlie, does not have to make a choice about different formalizations of F, as they would if the first approach was followed. This leads to a better and more consistent user experience. The second approach is not, however, without its downsides. The first is the added work Alice would need to do to improve F and modify existing formalizations dependent on F, compared to just redoing F for her own needs. There are two comforting remarks which can be given to Alice in this situation. The first is that others will have gone through the same pain and she is benefiting from their work. The second is that the process of having to adjust all of the results that depend on F to her improvements or changes would allow Alice to be sure she is not breaking any of the functionality of Bob's formalization. This thereby acts as a litmus test for Alice's changes. The second downside to this approach is the following. Suppose Bob has formalized F and is writing a paper on its formalization or related results, and Alice comes along and improves or modifies the formalization of F. The downside is the dilemma Bob now faces. Does Bob include Alice on his paper and or talk about Alice's formalization instead of his own? I believe the solution to such questions can be made on a case-by-case basis, as is currently done on a more local scale, but I also believe that some community guidelines could be created to potentially ease the worry of some authors who may want to formalize results but may be put off by such dilemmas. The third downside is related to whether Bob agrees with or consents with Alice's supposed improvements. Perhaps what Alice thinks is an improvement is, in the eyes of Bob, not. A solution to this problem is the subject of the next subsection. Section 4.3. Transparent peer review. Suppose Alice from the previous subsection improves and makes changes to Bob's formalization of F. Who decides if Alice's improvements are good enough to make it into 15 or not? There are two complementary ways of doing this. The first is to use automated computer checks to ensure Alice's work meets certain standards. The ITP itself will check for mathematical correctness. So these additional checks correspond to things like ensuring all definitions have documentation, not having unwanted double spaces, and ensuring correct indentation. Via the synergy of ITPs with GitHub and Visline, such automated checks are easy to implement using GitHub's workflows as mentioned above. The second way to ensure Alice's improvements are good enough is via a peer review process. The idea is the following. Suppose Alice submits her changes to F to the project. Another expert, Emma, say in F, would look at Alice's changes and determine their quality and if they are actually improvements. Emma would then give her advice to a team of maintainers about whether these improvements should be merged. The maintainers, like an editor of a journal, would follow that decision in all but the extreme cases. This is the exact process that happens in MATLAB and countless other open source projects, and it is again easily implemented via GitHub. I advocate for both these mechanisms to be present, as they not only maintain the project's quality, but they also act to prevent idiosyncrasies from emerging in different modules. Prevention of idiosyncrasies has the added benefit of increasing ease of user experience. Exploring the peer review process further, I believe there are two important features it should have. The first is speed. The change Alice made to F may only be very small, and Alice and others may be dependent on those changes for future work. If the review process takes too long, this may, depending on Alice's workflow, stagnate her progress, or worse still, she may lose interest in formalization entirely due to the burden of the peer review process. The second is transparency. Transparency is important as it not only aids to speed up the review process, but it ensures a level of fairness between contributors. In particular, a contribution to Fissling should be judged as systematically as possible on its content, not who wrote it. Section 4. Informal results. Suppose Alice is now a physicist who is an expert in an area E, but who, like most physicists, does not know how to use an ITP. I believe it should be possible for Alice to still contribute to the digitalization of physics using her expertise in E. This can be facilitated in a project like Fissling using the notion of informal results. Informal results are placed as temporary substitutes, perhaps long-term, for formal results within a project. An example of an informal result in Fissling is docstring. The time evolution of the Higgs parameter is equal to minus h squared 1 plus q. Informal lemma, time evolution Higgs constant, where dependencies are the Higgs constant and the tag is 6z3bs. Here the first line is an English statement of the result, line 2 contains the name of the result, line 3 the dependencies of the result, and line 4 a unique identifying tag which is used to produce a list of all informal results. The idea is that Alice would be able to write these informal results based on her expertise in E, in sufficient detail that, for example, Bob, who knows how to formalize results but is less familiar with E, can turn Alice's results into formal results. A similar concept has been used in the mathematics communities in the form of lean blueprints. These are LaTeX-generated documents which guide the formalization of results. An example of a project which is currently ongoing and using blueprints is the Fermat's Theorem project. The advantage of this workflow is that it can put to best use the expertise of individuals in the most efficient way. For example, there is no point Alice trying to formalize something when it does not meet her personal skill set. Having a project like Fissling allows the necessary infrastructure to be built around these informal results, making them easy to find and formalize as possible. Section 4.5. Integrating into knowledge resources. Historically, academic knowledge has sat within academic papers. With the advent of AI and its heavy reliance on datasets, there has been a proposal for a multi-purpose knowledge resource in reference 19. As mentioned in that paper, lean and ITPs can provide a well-founded way in which some human knowledge can be stored. An open source project like Fissling can be seen as a store or a supplier of such knowledge. Furthermore, the necessary infrastructure and standards could be built into Fissling to make interactions with such a knowledge resource as efficient and effective as possible. This will require engagement and collaboration between and across communities. When the foundations of such a knowledge resource emerge, I advocate for such a collaboration. Section 5. Motivating aspects of general usage. Beyond the argument for a single open source repository, Fissling, the thesis of this paper includes more general recommendations on how physicists can most effectively use interactive theorem provers. In this section, I give the arguments for each of these recommendations. Section 5.1. Including physics context. A definition or theorem in physics contains additional physics context beyond its mathematical statement. For example, it's possible to have two theorems or two definitions in physics which are mathematically the same statement but which carry different physics context. An explicit example of this is the Hilbert space of a qubit and the target space of the Higgs field. Mathematically, Both of these correspond to the vector space C2, but they correspond to physically different objects, i.e. when the physical context is included. When formalizing physics, I believe that it's important to include this physics context within the formalization to help the reader understand what is being formalized and why. There are a number of ways the physics context can be included in a formalization of an area of physics. The first is by ensuring the names of the definition or theorem matches the physics underlying it. For example, the name of the Hilbert space of the qubit could be qubit Hilbert space, whilst that of the target space of the Higgs field could be target Higgs field. Some ITPs will allow you to cast from qubit Hilbert space to target Higgs field, i.e. to treat an element from the former as an element of the latter. In a lot of cases, this does not make physical sense, and certain tricks can be played to prevent such casting, and in doing so, prevent physics mistakes being made. The second way to include physics context is via documentation. Like most programming languages, IDPs allow you to include documentation surrounding and connected to different parts of the code. For example, in Lean, one can give files a designated documentation string, which is usually used to explain their content. One can also give documentation strings to individual theorems and definitions. These documentation strings are usually used to give an English written description of a result. Such documentation can, and I believe should be used to include the physics context of the underlying result. Not only does this have the advantage when it comes to the user reading and understanding a formalization, but it also makes it easier to search for results, both with algorithmic methods, e.g. Lugal, or AI methods, e.g. Lean Explorer. These documentation strings can be supplemented with references to the literature connecting the formalized results to the informal results and related discussions. The last way to include physics results within a formalization I will discuss is through organization. Results related to the same area of physics or the same physical object can be placed together in the project. This should surpass an organization based on the mathematical context of a result, as is done in, say, MATLAB. Such an organization can make it clear what area of physics a formalized result is related to and what it is trying to achieve. This is related to the content of the next subsection. Section 5.2. Build APIs around data structures. Computer scientists are in general interested in data structures, for example, lists, arrays, and dictionaries. Thus, when building a library of results, they will often first identify the key data structures present, and then for each of these data structures create an API, i.e. lots of operations or functions on those data structures. These operations may not be of immediate use to the particular computer scientists, but may be of use to others in the future. This also influences the organization of the library they build. For example, a computer scientist may identify a list as a key data structure in their library. Thus, they may create a file which starts with the definition of a list and then defines sorting of lists, reversing elements, inserting elements, etc. In other words, define or create an API around lists. Enough data structure of interest to the computer scientist might go into a different file. This holistic approach of the computer scientist should be compared with the approach taken by physicists when writing papers. Typically, physicists will identify the key theorem or result they want to prove and just give enough definitions of surrounding context to ensure that key result or perhaps its proof makes sense. This, in a sense, is the opposite point of view of the computer scientist. It is not surprising that taking the computer scientist's approach is in the long run more useful when formalizing physics than taking the approach traditionally followed by physicists. The main reason for this is that it ensures that the results are present for future uses, and the building of an API acts as a test for the practicality of a given definition. To explore how this works in practice, let us give two examples from PhysLean. The first example is from quantum mechanics. For the 1D harmonic oscillator in QM, there are a number of data structures involved: the Hilbert space, the collection of physical parameters, and a set of solutions. In PhysLean, each of these data structures has its own file and API built around it. The second example is Wick's theorem from quantum field theory, the formalization of which was presented in reference 13. Here, there are a number of key data structures, the most important one of which is Wick contractions. A lot of the formalization of Wick's theorem in PhysLean is down to build in a large API around these WIT contractions, and this API sits in a clear, distinct file system within the project. The approach outlined here is the approach taken in MATLAB. However, I wish to highlight one important consideration that physicists should take into account. In some ITPs, Lean being one of them, it is impossible to create definitions which are not computable. In other words, cannot be put or used in computer programs which can be executed. This is often down to the presence of the axiom of choice. Mathematicians rarely care about non-computability, but physicists often want to make programs with their functions. As such, I believe it is important, where possible, to ensure that data structures the APIs are built around are computable. Similar to how AI can be used to write code into Python, and AI can be used to help write formalizations into an ITP. In some cases, the correctness or incorrectness of the formalization can be fed back into the AI, and the AI can adjust its formalization accordingly. This automatic feedback loop is why some companies like Google DeepMind and Harmonic are turning to Lean to help their AIs reason. In this section, I want to focus more generally on the use of AI in helping formalize physics, whether that be simply using LLM like ChatGPT or Lean-specific programs like Lean Copilot, which take advantage of the aforementioned feedback loop. I wish to argue that whenever an AI formalizes physics, a human should always act as a gatekeeper. This is not least because we should be formalizing physics for humans, and as such, humans should be in charge of deeming whether a formalization is useful to us. More practically though, even with the above feedback loop, there is plenty of room for AIs to hallucinate when formalizing physics. This is perhaps more an issue in physics than in mathematics, due to the additional physics context around the definitions and theorems that must be present. But the AIs can also hallucinate in the definitions themselves, and if they do, the theorems they end up proving may be theorems about the wrong things. The definitions the AI makes may only be practical for the given task the AI has been given, and are not more widely applicable. These hallucinations, if not kept in check, can serve to dilute the information quality of formalized physics, and it could eventually get to the point where it becomes unusable. Similar arguments can be applied to other programming languages and libraries, and more generally, the internet. Section 5.4, Physics-based theorem proving tactics. One key advantage of an ITP like Lean is that their tactics can help with proofs. These tactics, often written in a meta language, make ITPs easier and more enjoyable to work with. However, the tactics do not come free, they have to be developed and made usable. To give an example of a tactic, Lean has a tactic ring. The idea is that this can prove relations which hold due to basic properties of a ring, e.g. commutativity and associativity of addition and distributivity of multiplication over addition. For example, if A, B, and C are of type A and A carries an instance of ring, then the tactic ring will be able to solve A times by B plus C equals C times by A plus B times by A. There are data structures of particular interest to the physicists, for example Feynman diagrams, Lagrangians, gauge fields, etc., some of which have automated tools to use and manipulate them in other languages like Mathematica. I will argue that effort should be put into developing such tools. More generally, I argue that whenever a physicist makes a data structure, they should ask themselves if there are any tactics which would make working with that data structure easier. In some cases, the time and effort needed to make such tactics will not be worthwhile, and in others, it may constitute its own research project. But in general, there should be a research effort to develop in these tactics.